In the last lecture, we had talked about expressions and operators with side effects. In today's lecture, we'll discuss a very important aspect of all programs, that is input and output. We have already seen how basic input and output of data is done in the simple programs that we have written so far. Today, we'll go into some more details of how input and output is done in C. So, C has no built-in primitives or statements for input and output. For all input and output, that is I/O, we have to use library functions. We have already seen several of these library functions in action. For example, we have seen scanf for reading values from the terminal and printf for printing some output on the terminal. In this lecture, we will restrict ourselves to input and output only from the terminal. Although in general programs need to read data from and write data to files as well, but we'll discuss that in later lectures. Today we'll restrict ourselves to input and output from the terminal only, but as we'll see, using something called I/O redirection facilities of Unix, we can actually use the same techniques to do simple input and output from files as well. So the two library functions for input that we are going to discuss today are scanf and getcar. Scanf we have discussed, we have seen examples of usage of scanf already, and the output library functions that we will discuss today are printf and putcar. Again, printf we have seen some examples of. Okay, so let's start with the printf function. As you know, this is used to print some data on the terminal. We have seen several examples of usage of this function. The first argument is what is known as a format string, which specifies essentially what is going to be printed on the screen and how it is going to be formatted. The format string may contain ordinary characters like alphabets and numerals or other special characters which are printed as they are on the screen, as they appear in the format string. Plus, we can have escape sequences such as \n for the new line character and so on. And when we want to print some values whose actual value is not part of the string but is specified by some expression which is an additional argument to printf, we use what is known as a format conversion specifier, which starts with a % character in the format string. The % character specifies that a value to be printed is supplied as an additional argument to the printf function, and the character following the % character in the format string specifies what is the type of the value and how it is to be printed. So we have already seen examples of %d. When we use %d in the format string of printf, then the argument which follows is assumed to be of type int and it is printed like an integer. If we want to print an unsigned int, we should use %u instead, and similarly %ld for long, %ul for unsigned long, %st for short, %hu for unsigned short, %f for double, %lf for long double, and so on. The %c specifier says that the corresponding argument is of type integer, but it is not to be printed as an integer, but the character whose ASCII code is this integer, that character should be printed. We'll see examples of this. And since % has a special meaning in the format string, if we want to print the % character itself, we can use %% to indicate that we want to print 1% character. So here is a simple example which demonstrates some of these specifiers that we have seen. So in this example, we have several variables. The variable c is of type char and is initialized to the character a. Remember that a variable of type char is actually an integer, and the value assigned to the character c in this initialization is the ASCII code of the character capital A. I is a variable of type integer with the value 5, x is double with value 5.0, y is a float with value 10.0. Recall that literal constants of this type have by default a type double, and we have put an f after it to indicate that we want this value to be of type float. Now here is the printf statement, and this first argument here is the format string. Now this has a %d, %c, %f, %f. And since there are 4 format conversion specifiers, %d, %c, %f and %f, there have to be 4 arguments. Now, the first argument corresponds to the first argument following the format string, that is, corresponds to the conversion specifier %d, and so therefore it should be of type int. We have given the expression here as simply I, which means that the value of I will be printed as an integer, that is the value 5 will be printed. And then the next specifier is %c, which means we want a character to be printed, and the corresponding argument, that is the second argument following the format string, has to be of type int, and it should be the ASCII code of the character that we want to print. Now C happens to be of type char actually, but what is expected is an int. So therefore we have to explicitly say that we want this C, this value to be converted to a value of type integer. So that is why this int within the brackets indicates that we want this explicit type conversion to be done. This is also called type coercion. We have already seen that in expression sometimes automatic type conversion happens if the operands of a operator happen to be of different type and so on. Sometimes we also need to explicitly perform type conversion, and in this case it's called type coercion. The third argument is x, which corresponds to the %f here, and %f requires the corresponding argument to be of type double, which x is, so that's alright. But the next one is again %f, which means that we have to supply a double. What we want to print is y, which is of type float, and so therefore we have again explicitly converted this value to double by doing a type coercion here. So these two are examples of type coercion. So what will the output look like? Well, this %d in the format string will get replaced by the actual value of this integer I, which is 5, and then after that the character corresponding to the ASCII code, character whose ASCII code is supplied as the next argument will be printed. That happens to be A. So A is printed. Note that there is no blank between 5 and A because there is no blank between %d and %c in the format string. And after that the two double values will be printed, which are 5.0 and 10.0. So it's important to understand at this point in time what exactly is going on when we are using printf. Now it turns out that when we do input and output, that input and output can always only be in terms of characters. Only characters can be printed on a terminal, right? So that means that to print anything on the terminal must be sent a sequence of characters, that is ASCII codes of characters, and the corresponding characters are what are going to be printed on the terminal. So therefore, if you want to print the integer 50, then we have to send 2 bytes to the terminal. The ASCII code for the character 5 followed by the ASCII code of the character 0. The ASCII code of character 5 happens to be 53 and the ASCII code of the character 0 happens to be 48. So therefore, to print the integer 50, actually 2 bytes, which are 53 followed by 48, have to be sent to the terminal. But internally the integer I is represented as the binary equivalent of the decimal number 50, right? So this conversion has to happen, and this conversion is what is being done by the useful library function printf. And the way it performs the conversion, it is guided by the conversion specifier. For example, %d says that an integer is specified and it has to be converted to a sequence of bytes corresponding to the digits in that integer. Okay, let's now come to a simpler output function, that's the putchar function. So this function can be used instead of printf when we want to print just one single character on the terminal, and we would usually prefer to use putchar instead of printf because putchar is usually faster. So if what we want to print is just a single character, we can use putchar instead of printf. The argument to putchar is an integer of type int, which must be the ASCII code of the character that we want to print. So for example, if we want to print x on the terminal, then we can use this kind of a statement. Putchar within brackets int followed by within quotes x. Now this within quote x, remember, denotes the ASCII code of the character x, but the type is char. Since putchar expects an integer as an argument, we have explicitly converted it to an integer before supplying it to putchar. So this statement will print x on the terminal. Let's now look at the scanf function for reading input from the terminal. Scanf is the analog of printf for input. Again, the input is in terms of characters only. Now, what we type on the keyboard when we are supplying input as a user are characters. For example, when I type 5 and 0, what is actually being sent to the program is a sequence of 2 bytes, which is the ASCII code of the character 5 followed by the ASCII code of the character 0. Now, if I want this value 50 to be stored in an integer variable, we must convert this sequence of ASCII codes into the binary equivalent of the decimal number 50. So this reverse conversion is what is being done by the scanf function. The usage of scanf we have seen earlier in examples. It's fairly similar to printf. The first argument again is a format string which specifies how the input is to be converted, whether we expect an integer or a real number or whatever it is, and the remaining arguments specify where, that is in which variables, this input data is to be stored. So the conversion specifiers for scanf are fairly similar to those for printf with some minor differences. For example, %d reads an integer. Now what that means, remember, is that it reads ASCII code, it reads characters and expects characters which constitute an integer. For example, an integer really means that you should have optionally a plus or minus sign followed by a sequence of digits. And scanf, what it does is it reads characters, skips initial white space characters. White space characters are like the blank character or the new line character or the tab character, and it starts converting once it finds a character which could be part of an integer. So a plus or a minus sign or a numeral, and then it keeps reading till it reaches the end of the number and then converts the sequence of characters that it has read so far into a single integer and assigns it or stores it in the variable which is supplied as the corresponding argument for the conversion specifier. In this case, the argument must be a pointer to a variable of type int. We haven't really discussed what pointers are. We will discuss that in subsequent lectures later on. But a pointer to a variable essentially is obtained by prefixing the ampersand sign before the variable name. So in usages of scanf, as we have already seen, that the arguments after the format string are ampersand followed by some variable name. So this ampersand is required because the argument must be a pointer to a variable of the appropriate type. So in this case, I must be an integer, and we have to use first ampersand I as the argument for scanf corresponding to %d. There are minor differences from the printf specifier. For example, %f is for float instead of double, and %lf is used for double instead. Similarly, for %c, the corresponding argument must be pointed to a variable of type char, not int. And in this case, what happens is that scanf reads a character and assigns its value, which is the ASCII code of the character, to the variable which has been specified. Note that no characters are skipped in this case, as opposed to when reading an integer. When reading an integer, the initial white space characters are skipped. But when you're reading a character, no characters are skipped because even white space characters are characters. So if the first character type was a blank space, for example, the variable will be assigned the ASCII code of the blank character. The getChar function is similar to the putchar function. It can be used when we want to just read a single character from the input. There are no arguments. The return value, which means the value of the getChar expression, is of type int, and it is simply the ASCII code of the next character in the input. So for example, if you want to read just one character from the input, we declare a variable x of type int and use this kind of an assignment statement x assign getChar. This will read the next character from the input and assign its ASCII code to x. Note that when a character has been read from the input, the next time when we call getChar again, it will return the next character in the input. That is, the character which is read here has been in some sense consumed by getChar. So when we call getChar again, or indeed scanf or any other function for reading from the input, then this character, since it has already been consumed, is no longer available. So for example, if the user types XYZ and then we call getChar 3 times, then we successively get the ASCII codes for the characters X, Y and Z. Right? One important point to note is that the variable which is used to store the return value of getChar must be of type int always. We will come to the reason why this is so in a little while, but never use a variable of type char or something else to store the result of getChar. Okay, let's now use what we have learned today to write a couple of simple programs. In the first example is particularly simple. All you have to do is to write a program which copies its input to output. That is, whatever is the input, the output is exactly the same. So the way we are going to write this program is fairly simple. We are going to use getChar to read characters again and again. We'll put this in a while loop till the end of input is reached. And for each character read, we'll use putChar to output it. Now, how do we know that the end of input has been reached? We'll know that when getChar returns the special value EOF. EOF stands for end of file, so this indicates the end of input on the terminal as well. And on the terminal, how does the user indicate that he is finished giving the input? Well, he does that by typing Ctrl D on a line by itself. Now, the reason, as I said earlier, the return value of getChar should be stored in a variable of type integer is that the value EOF is -1. It's a negative value. So that is why it must be stored in an integer. Okay, so let's now see this program and try to execute it. Okay, here is the program. It's a very simple program, but there are some instructive points about this program. So we declare a variable of type int, we call the variable C. This will hold the characters that we read from the input one by one. And this loop says read a character, if it is not end of file, use putChar to print the same character. Note that we have used an expression with side effect in this particular loop condition. So if you look at this particular expression, C assigned getChar, what it does is that it calls getChar to get the ASCII code of the next character that is assigned to the variable C, and the value of this expression itself is the value that has just been assigned to the variable C. Now that value is what is compared against EOF, and if that value is not EOF, that is end of file has not been reached, then we use putChar to print the character C. So this is a very common idiom, and this often simplifies the loop condition to use assignment to a variable and then compare the value that has just been seen with something else. Okay, so let's now run this program. I have already compiled this. So let's give some input. You can see that we have typed several characters, but no output has appeared so far. Output will appear as soon as we press the return character. As soon as we press the return character, you see that all the characters that we have typed so far, they appear on the output, exactly the same as they were in the input. Let's give some more input. And when we want to indicate the end of file, we can simply press Ctrl D on the line by itself. That will cause getChar to return the EOF value, and which will terminate the loop and the program will exit. Okay, now we have written this program to read input from the terminal, but Unix has a facility called InputOutput redirection, using which we can make the program believe that its input is actually coming from the file. So, for example, if we use this notation to execute the program, we need some input file. So let's say copy.c itself. then the contents of the file copy.c, which is the program that we just wrote, has been printed on the screen. So what is happening in this case is that the input is coming from this file. The program doesn't need to change in order to do that. The operating system ensures that when the program reads from what it believes is the terminal, the input actually comes from the file. And of course, the file does not need to contain the control D character, because the file has a finite length, and when it finishes, the end of file is indicated to the program by the operating system automatically. So this way we can actually we can write any program that is expected to take input from the terminal, and we can supply it input from a file instead. And similarly, we can actually redirect the output of the program to a file instead of the terminal. So, for example, suppose we do something like this. So in this case, what we are saying is this greater than sign says that the output of the program is being redirected from the terminal to a file called xxx. That is, whatever the program prints as output will not appear on the terminal, but will go in this file instead. So let's give some input. You see that it does not appear on the terminal at all. And if you see now, we already have a file called xxx. We can see what the contents of this file are. This is exactly what we typed as the input. And in fact, we can combine both input and output redirection. Let me first delete the file xxx. We can actually combine the input and output redirection both, so that the input comes from a file and the output goes to a different file. If we do that, we can actually use the program that we just wrote in a very useful manner to copy files. So for example, we want to make a copy of the file copy.c. We can do this like this. So what we are telling the operating system in this case is that when the program copy is run, its input should actually come from the file copy.c, and its output must go to the file copy2.c. Of course, you must not use the same file name for both the input and the output redirection. That will just corrupt both the files. So if we just do this, you see that there is nothing that appears on the terminal, and we didn't have to give any input either. But the file copy2.c now contains a copy of the file copy.c. So we can use, as you have seen, the copy program, the very simple program that we wrote to see the contents of a file by doing input redirection. We can use it to enter some contents into a file by doing output redirection, and we can use it to make a copy of a file into another file by doing both input and output redirection. So as we saw, one of the observations that we made by executing this program is that for input from the terminal, the program receives the characters only after the user ends the line. We saw that as soon as we typed a character, it didn't appear again on the output. That's because the program received all the characters that we typed only after we ended the line by pressing the enter key. And similarly, although it's not really apparent from this execution, the output also appears only after a new line is printed by the program. So this is called buffering, which is done by the operating system. And we have seen that programs that read input from the terminal and print output to the terminal can be used with files easily using the IO redirection facility of Unix. In later lectures, we'll discuss in more detail how the program can directly work with files, because in many cases the simple IO redirection is not sufficient. The program may want to open and read several files and write different outputs to different files and so on, in which case the simple IO redirection facility is not sufficient, but we'll come to that in a later lecture. Okay, here is example 2. We want to write a program which counts the number of characters, the number of words, and the number of lines in the input. How do we do that? The idea is very simple, similar to what we have just seen. We again read the input character by character. How do we count the characters? That is quite easy. For each character that we read, we increment the character count by 1, which is of course initialized to 0. for each new line character that we see, that is the \n within quotes, that's how we'll use it in our program, we increment the line count by 1. So we are maintaining a word count, a character count, and line count in 3 different variables, all 3 initialized to 0. And for each character seen, we increment the character count by 1. For each new line character that we see, we increment the line count by 1. But what about words? Well, we'll assume that the words are separated by white space characters. Between two words, there must be some white space characters. Any number of white space characters. Remember, white space characters are blank character, the tab character, and the new line character. So how do we count the words? Well, what we are going to do in this program is that we are going to increment the word count when a new word starts. Now, when does a new word start? A new word starts when we see a non-white space character followed by a white space character. That means that a new word has started, where a white space character, of course, is a blank or a new line or a tab. Or a word also starts if the first character in the input itself is a non-white space character. For example, if the input starts with the character X, then a word has started, so we must count that as 1. Okay, so which means that in addition to storing the current character that we are processing right now, we must keep track of whether or not the previous character was a white space character. Because if what we have just seen is a non-white space character, then we must increment the count only if the previous character was a white space character and not otherwise. Because if we have a blank followed by X followed by Y, then when we see the X, we should increment the word count. But when we see the Y, we must not increment the word count because it's not part of a new word. So how do we keep track of whether the previous character that we saw was a white space character or not? That's very easy. We can use a Boolean variable to keep track of that. So we'll use this Boolean flag to keep track of whether the previous character was a white space character or not, and we'll have to initialize it properly. Initially it will be true because if the first character itself is a non-white space character, we must assume that it is starting a new word and therefore count 1. So we'll initialize it to true, and subsequently it will be true or false depending on whether the previous character that we saw was a white space character or not. Okay, so let's look at this program now. Here is the program. This is a slightly more complicated program, so note that I have put a large comment which describes what the program does. We are going to use, of course, integer values 1 and 0 as true or false. So we have, as per our usual practice, put defines for true and false. Okay, and here the main program starts. There are 3 variables: lines, chars, and count. Lines, chars, and words. These are the counts of the lines and the characters and the words that we have seen so far. They are all initialized to 0. Now this inspace is the Boolean variable that we are talking about, and this is meant to be true initially and when the previous character that was seen was a white space character. Remember that a Boolean variable can be implemented by using any integer type. So we have chosen to use the type char. We could have used an int or a short instead. That would be perfectly fine too. So inspace is going to be true if the last character seen was a white space character, and it will be true initially, otherwise it will be false. And this variable c of type int, of course, is the variable that will hold the ASCII code of the character that we have just seen. The loop condition looks very similar to what we had for the copy program. We read a character and compare it with end of file. If we get the end of file as a result of calling getChar, then the loop terminates. Otherwise, c is assigned the character that we have just seen, and we proceed to execute the loop body. So now, the first thing that we do is increment the character count. We have seen one more character, so immediately increment the number of characters that we have seen so far. And if what we are seeing is a new line character, then we increment the number of lines seen so far. That part is very easy. What remains is to figure out whether this is a new word which is starting or not, and appropriately update the inspace Boolean variable. So for doing that, we need to first figure out whether the character that we have just seen is a white space character or not. So if c is equal to the blank character or the tab character or the new line character, then we have just seen a white space character. In this case, we need to set inspace to true. Note that it might have already been true because the previous character we saw might also have been a a white space character, but that doesn't really matter. Whenever we see a white space character, in space must be true in the next iteration, so that's why we are making it true. Otherwise, if we have seen a character which is not a white space character, now we have to decide whether this is the starting of a new word or whether it is the continuation of an old word. And the distinction between the two is that a new word is starting if the previous character was a white space character. In other words, if in space was true earlier, then this is the starting of a new character, of a new word. Note that in this case we have not changed in space to true. We have changed in space to true in this iteration only if this character was a white space character. And of course a character cannot be both a white space character and a non-white space character. So if in space is true, that means that what we have seen is either the first character in the input or the previous character was a white space character. And now of course in space should become false, because certainly this character is not a white space character. So in the next iteration of the loop, in space must be false, so that if we encounter another non-white space character in the next iteration, we don't count that as the beginning of another word. And since this has begun a new word, we must increment the count of the number of words. Note that we have used the increment operator plus plus to increment the values of lines, chars, and words by 1. We have already seen what this operator does in the previous lecture. It increments the variable, and this is a post increment. So what it returns is the old value of the variable. But in any case, we are using this as a statement, and so therefore we are discarding the value of the expression itself. And depending on the preference, we could have used the pre-increment or the post-increment operator. The result would have been exactly the same, because the side effect of both is to increment the variable by 1, and the return value is the only thing which is different, and the return value or the value of the expression is being ignored in this particular case, in any case. So that's all there is to the program, and when the loop ends, we have the count of the characters, words, and lines, so we can just print that. So we printf using this format string. So in this format string, note that the characters C, H, A, R, S, colon, blank will get printed as they are. The characters %d will be actually replaced by the value of the variable chars here. And again, these characters get printed as they are. This %d is replaced by the value of the variable words. These characters get printed as they are, and this %d gets replaced by the value of the variable lines, and this new line character is printed as it is, which means that the cursor comes on to the next line, and the program ends. So let's now try out this program. I've already compiled it again, so let's just execute it, and let's give some input. We already know how to terminate the input. Note that no output will appear till we actually end the output, because we are not outputting anything for every character in the input. So let's terminate the input now. What this says is that there were 104 characters that we typed. Note that this will include the blank spaces and the new line characters that we typed. Number of words is 17. We can count that easily enough to ensure that this is correct. On the first line we have 5 words, 6 on the second one, that's 11, and 6 on the third one, that makes it 17, and there are 3 lines. And again, we can use IO redirection to count the number of words in some other file, in some file. So as before, let's count the number of words in this file wordcount.c itself, which contains the program that we just wrote, and the program tells us that this file contains 985 characters, 178 words, and 41 lines. And we can actually verify this output by using the standard word counting utility in Unix. So there is a program called WC which does pretty much the same as our simple word count program. So we use the standard WC utility to count the number of words, lines, characters, etc. in the file wordcount.c. We find that we get the same output. The WC program prints the number of lines, then words, and then characters. So we see that it said 985 characters, 178 words, and 41 lines, which is precisely what our program also produced for the same file. Okay, so at the end of the lecture, here is a simple exercise for you. Rewrite the copy program yourself, but this time we want to make small changes to it so that the case of all alphabet letters is changed. That is, all lowercase letters in the input are converted to the corresponding uppercase letters, and the uppercase letters in the input should be converted to the corresponding lowercase letters, and the other characters like special characters or blanks or new lines, etc., should remain as they are. Now here are a couple of hints for to help you with writing this program. So we need to do two things in this program really. When we read a character, we need to check whether or not it is a lowercase letter. If it is a lowercase letter, then we need to output the corresponding uppercase letter. And similarly, if the character happens to be an uppercase letter, we need to output the corresponding lowercase letter. And if the character is neither lowercase nor uppercase, then we output the character as it is. So now how do we check whether, for example, the character C is a lowercase letter of the alphabet? We don't need to compare the value of C with all the lowercase alphabet letters from A to Z, because remember that in the ASCII codes of the various characters, the codes for the characters A to Z are one after the other. That is, the ASCII code for B is one more than A, then the ASCII code of the character C is one more than the ASCII code of character B, and so on and so forth. So given this property of the ASCII codes, it is enough to check that if C is greater than equal to the character A and it is less than equal to the character Z, then it must be some lowercase letter. And similarly, we can check whether a character is an uppercase letter or not. So having checked whether a character is, let's say, a lowercase character, we need to find the corresponding uppercase letter. Now, how do we compute that? Now, again, we use the same property that the ASCII codes for small a to small z are contiguous, and similarly ASCII codes for capital A to capital Z are contiguous. Now, which means that if C is indeed a lowercase letter, then if we subtract the ASCII code of A from it, then what we'll get will be the place of the letter C of the character C in the alphabet, starting with 0. So if C happened to be the character A itself, this will give us 0. If C happened to be character B, this will give the value 1. If it happened to be character C, it will give the value 2, and so on. And remember that we can do this arithmetic on characters because characters really are nothing but small integers. We are only storing the ASCII codes of these characters. So once we know this, the place of the particular lowercase character that we have seen in the alphabet, now to that place value, if we just add the ASCII code of capital A, that will give us the corresponding uppercase letter. For example, suppose C happened to be the lowercase letter D. Now D minus A will give us the value 3, because D minus A will give us 1, C minus A will give us 2, and D minus A will give us 3. And if we add 3 to the ASCII code for character A, that will give us the ASCII code for the character D. So this way we can find out what is the ASCII code for the uppercase letter corresponding to a certain lowercase letter, and similarly if we want to find the lowercase letter corresponding to an uppercase letter, the procedure is similar. We subtract the ASCII code of capital A and add the ASCII code of small a. So this finishes today's lecture. In the next lecture we will start looking at the control statements like the if statement and the while statement and so on in more detail, and we will introduce some more useful control statements.